pure flow, fluid flow. I'm also giving in this table the considered nanoparticles in this study. See, their thermophysical properties are also given here as compared to pure water. So copper has such properties, thermophysical properties, copper oxide, silver, and aluminum and titanium oxide, right? The present linear stability analysis is mainly confined to two-dimensional flows, although it can be generalized to three-dimensional flows. And I'm also giving you I will also give you example on that anyway. In line with the hydrodynamic stability theory of pure fluid flows, the basic flow of nanofluids obtained in equation 4 is perturbed by adding infinitesimally small disturbances like U prime and V prime. So these are very small disturbances. So by adding such small disturbances, you can linearize your system 1. And this is the linear equation then as a result of linearization. So I'm introducing Reynolds number, which is the classical Reynolds number, but it is Reynolds number of nanofluid, in fact. C, it is UCL over nu NF. And UC and L are being reference length and length scales, reference velocity and length scales. And well, in parallel flow, if you assume parallel flow, then the vertical component of velocity disappears because it is negligible. So this system by cross differentiating can leads us to this equation 7, which is called, in fact, Or-Sommerfeld equation, whose form after wave-like normal mode assumption 8 gives us this fourth order differential equation, C in equation 9. So it is just fourth order differential equation regarding amplitude of perturbations. And here V bar is just amplitude of nanoperturbations, alpha is the wave number of perturbations, and omega is the frequency of nano disturbances or perturbations. These are necessarily real. These are not necessarily real, but they can be complex, right? In general, and in the limit of Reynolds number tending to infinity, that Or-Sommerfeld equation evolves into the well-known inviscid Rayleigh stability equation, which is a second-order equation of this type. Okay, so this is my linear stability equation in this case, in the inviscid case. It should be remembered that the viscous inviscid instability equations 9 and 10, which Or-Sommerfeld and Rayleigh equations, are accompanied with vanishing perturbations at the wall and also at the far field, because we are assuming that very small perturbations are introduced into the main flow and they disappear at the wall because of attaching to the wall property, and also they disappear at the out of the boundaries. In some special circumstances where the base flow has no dependence on the nanoparticle phi, it is sometimes possible to resolve the eigenvalues from the formal eigenrelation delta, alpha, omega, Reynolds number, some other physical parameters, all depending on the nanoparticle volume fraction phi. So this is just eigenrelation, okay? Setting phi 0 gives us the stability of pure fluid, namely delta alpha f omega f Reynolds number f equal to 0. So this is just dispersion relation regarding pure fluid without nanoparticles. Usually the neutral curves regarding the real eigenvalues are drawn to determine the boundaries of growth decay of the disturbances. To illustrate, say the pure fluid UB in the absence of nanoparticles has the represented neutral curve as shown in figure 1. See in here, I'm illustrating a classical neutral curve here. Inside this curve, the flow becomes unstable because perturbations will grow. Unstable means that your main flow will be disturbed and it will be destroyed anyway at the end. So laminar flow will turn out to be turbulent after some stage, some critical stage. So here, in fact, this is very important parameter here, the critical value of Reynolds number. So it gives us location of stability and instability, right? So before this parameter, everything is quite good and the flow is stable. Otherwise, it becomes unstable. Okay. So if a particle nanofluid is considered with a given nanoparticle phi, it is expected that the corresponding nano mean profile solved as a result of system equation 1 will be either stabilizing or destabilizing in accordance with the displayed figure 2a and 2b. See, I'm giving you some scenarios here regarding how stability and instability occurs under addition of nanoparticles. So in this case, in the first figure here, critical Reynolds number is higher than the critical Reynolds number of fluid, pure fluid. So it means that nanofluid here acts in terms of stabilizing your flow, your fluid, your system anyway. Because the critical Reynolds number is getting larger in this case, so the more part of the fluid becomes stable. Sometimes it is not always this case, but sometimes critical Reynolds number is lowered. So in this case, it means that nanofluid is now in favor of destabilizing, not stabilizing in this case. So it causes many. It causes instability in this case, right? If this is the scenario, it is causing instability. Otherwise, it is causing stability in this case. Okay. Okay, I'm now giving you two simple, very easy theorems, and relating the Reynolds. One is relating the Reynolds number of nanofluid to that of a regular fluid, which is given by this theorem 1. So it says that the Reynolds number Re of a nanofluid is proportional to the Reynolds number of the standard fluid. So it is the proportional to constant is given by this equation 14. So it tells you that Reynolds number of nanofluid is depending on Reynolds number of fluid by this coefficient, which is the division of ratio of densities to the ratio of viscosities. It is clear that this adjusting factor describes the Reynolds number of nanofluid once the Reynolds number of classical working fluid is known. So this is in line with the expectation that the critical Reynolds number of a nanodisturbance will be readjusted accordingly by the adjusting factor C, just obtained in 14. So that in terms of viscous instability, the nanoparticles may stabilize the regular fluid when C is bigger than 1, as outlined in figure 2a, or they may be destabilizing when C is less than 1. Okay. we should remark here that the corresponding exact shape of the neutral curve in both cases is required to be numerically computed. Otherwise, I'm just giving you just scenarios. But critical Reynolds numbers are exactly what you will find from numerical computation anyway. So as far as the practical need is concerned, the nanoparticles obeying shape factor bigger than 1 are preferred, because in this case they will cause viscous stability by pushing the critical Reynolds number to higher values. So the nanofluids presented in table 1 satisfy this requirement as revealed in figure 3. So this figure 3 says that the shape factor is bigger than 1, as you see, for all those nanofluids considered in this study. In fact, there is a critical case here considering aluminum oxide nanoparticles, and also there is a critical case for titanium oxide nanoparticles here. Otherwise, for other nanoparticles, C is always bigger than 1. So these are what this tells you, that such types of addition of nanoparticles will stabilize your flow up to volume fraction of 0.1, almost 0.1, right? So it is just stabilizing. Otherwise, if you add aluminum oxide nanoparticles of size bigger than 0.1, your flow may be unstable, right? Okay, so I'm just saying this here. Now, a natural question arises now: how can one assess the effects of volume fraction phi on the rest of the eigenvalues alpha and omega of a nanofluid disturbance? In general, as the nanoparticle concentration changes, the mean flow of the nanofluid will be redistributed throughout the flow field, slightly varying from its base state. With this new mean flow and the new adjusted Reynolds number of the nanofluid, it is necessary to compute the values of alpha and omega of the nanofluid from the system or Summerfield equation or implicit Rayleigh equation. Of course, we have to numerically solve in most cases. However, similar to the scale found in equation 13 for Reynolds number, it may also be possible to rescale the alpha and omega in a similar fashion introduced in equation system 15. So I'm saying that maybe there's a relation maybe there's a connection which relates wave number of nanoparticle to the wave number of fluid by this relation, and this is my adjusting factor F alpha or rescaling factor F alpha. And it is similar for frequency also, right? Maybe we can find such relations so that inserting such relations into a system of stability equations would yield again 10 and 13 with 12 with the adjusting factors F alpha and F omega in there. Having determined these, we will then estimate wave numbers and frequencies of nanofluid in terms of corresponding pure fluid. And this scenario is given by this theorem. I'm saying that if dispersion relation of nanofluid is proportional to the dispersion relation of pure fluid by proportional constant of F alpha, F delta, in that case, the effective eigenvalues of alpha and omega of a nanofluid can be estimated from this equation, this system 15 and 16. Well, this is very clear because in the case of pure fluid, dispersion relation will disappear, and it will also lead to disappearance of dispersion relation of nanofluid, right? Okay, now I think it's time to give you some physical experiments, explaining how my theorems are working on these real life problems. Okay, we now demonstrate hydrodynamic stability theory of nanofluids outlined in preceding section on several fluid mechanics problems. The first problem is, okay, first implicit flow examples. The first problem is very well-known classical fluid mechanics problems, which is breakup of a nanoliquid jet into droplets. Well, it is observed in every house of ours anyway. When you open a tap or face it, you know, the physical phenomenon is given here anyway in this figure 4, and to comply with the terminology in the literature, I'm just changing my frequency of perturbations into S by this relation omega equal to IS, and you can find the eigenrelation of such a problem in this paper, in this book by Drazin, 2002, given by this equation 17. So it relates eigenvalues alpha and eigenvalue omega of this breakup problem. Okay, so in this problem, A and gamma are radius and surface tension of thread liquid. Moreover, function I0 is just the Bessel function. And I'm saying that if you introduce adjacent factors Fs in this form and F alpha as 1, and then this theorem 2 will be satisfied, and accordingly the growth rate of disturbance, which is this thing of nanofluid, exhibits a decay from its pure fluid case without nanoparticles, implying that introducing nanoparticles will just lead to stabilizing effects. This in turn would cause an absolute delay in the breakup process in time, since this shape factor is less than 1, as can be witnessed from this figure. And then C, in this part B, I'm also showing how the growth rate is decreasing as you increase the volume fraction. And I'm just showing for two type of nanoparticles, for carbon and aluminum type of nanoparticles. Yeah, of course, you can yourself check other particles also, that growth rate is decreasing. I was wondering whether it would be possible to completely eliminate this growth rate and then let it vanish. It was possible, but in that case, mathematically, you need to add you need to consider phi as big as 0.5 or 0.6. But in that case, it is not physical, because in that case, other sort of stability problems would occur. And so physically, physically, I think scientists discussed that this nanoparticle size shouldn't be bigger than 0.5 anyway, to conserve some real stability cases. So what I'm saying here is that for this problem, introducing nanoparticles increases density necessarily, and then it delays the Rayleigh-Proto instability by increasing inertia. And then we noticed the damping will be accelerated most by silver type nanoparticles, and then least by aluminum oxide type nanoparticles. So in the second example of implicit problem, I'm considering parallel immiscible nanostreams, and which leads to Kelvin-Helmholtz instability. We now consider two horizontal parallel infinite nanostreams of different constant velocities and densities which do not mix, whose physical properties are illustrated in this figure here. So I have two types of fluids, one resting on the top, having density rho NF2 and pressure P2, and moving horizontally with velocity U2, and the one on the bottom having density rho NF1 and pressure P1 and moving at a velocity of U1. Okay, and they are not allowed to mix anyway. Here I am giving you a very simple basic state of this problem, and we present in fact two different situations. The one under internal gravity waves, when the velocities are simply assumed to be zero. In this case, the eigenrelation is given again in the book by Drazin in this form 20. Okay, and we observe that if we take the shape factor of frequency in this form, depending on shape factor of wave number in this form, in that case theorem 2 is satisfied fully. Therefore, normalizing the perturbations by f alpha to the power 1/2, we get the adjusting factor fs from 21, and the result tells us that addition of nanoparticles in this case is also stabilizing, as seen from figure 6 here. See, it is less than 1. It means that your perturbations will not grow by addition of such nanoparticles, right? Okay, there is also a second
Professor
scenario here.
Mustafa,
Yes.
Professor Mustafa, you have 5 more minutes left,
Yeah,
please.
I know. I should be quick, more quick. I'm giving you now viscous example problems. Well, the classical Rayleigh-Bénard convection problem, as can be found in many classical fluid mechanics books. In this case, Rayleigh number is defined as by equation 25, and I'm showing that this Rayleigh number also, Rayleigh number of nanoparticle also depends on Rayleigh number of fluid by a factor of Cc here given by this equation 27, and this equation 27, when you analyze here, it tells you that there is stability here. That means less convection occurs. Otherwise, if you add slightly higher nanoparticles of volume fraction bigger than 0.5, convection will be enhanced in this case here, right? So, okay. Again, a breakup of nanoliquid jet into droplets under viscous effects is similar to the in this case anyway. So here I am giving you some bounded and unbounded flow cases. A nanofluid flow over flat plate, which is Blasius flow, as you may know already. So these are classical equation of basic state, and or Summerfield equation and Rayleigh equation here. Well, if you take shape factors as I define here in system 34, in that case theorem 2 will be satisfied, and you will have viscous stability problem in this case. And as you introduce nanofluids, they will lead to viscously stable flow in this case, because well, it is clear from this equation, sorry, not in this in that part, because since square root 2c is bigger than 1, as seen in figure here, as in this case, it will be stable, right? And I'm also giving you example for nanofluid flow or rotating disk, whose equations are were solved by myself also here. So this is three-dimensional flow. In this case, I have three-dimensional flow. if you introduce now nanodisturbance by addition of normal modes of three-dimensional here, as in here, you have now alpha, beta in azimuthal direction, and omega as frequency. And neglecting Coriolis forces, you can also get Orr-Sommerfeld type equation, which was already done in 1981 by Malik, and you get this type of equation. Or if you in the limit of high Reynolds number, you get Rayleigh implicit equation like this, second order. And I'm saying that you should, if you get adjusting parameters like this, then you can estimate how your nanofluid will behave, or how your nanofluid will be affected by stability or instability. The more interesting part is here that the number of spirals, which is given by this equation, beta times Reynolds number, which is, I think, 13 in the case of pure fluid, will increase. Number of spirals will increase in the case of adding nanoparticles. But another interesting phenomenon is that their orientation is not affected at all. Okay, I'm also giving you nanofluid flow between two parallel plates, and all it says that from my estimations, you can just understand why addition of nanoparticles should be act in terms of stabilizing the flow. In fact, I estimated this
It's
from
the
my. Yeah,
last
thank you.
minute.
I will finish. See, from very simple correlations in my estimations, I just predicted that flow will become stable. This was implemented through numerical simulations in this paper by Lin and Hank. And indeed, they showed after very heavy numerical simulations that they show that indeed addition of nanoparticles will be stabilizing, because by critical Reynolds number in each case will be reduced. See, these are from these are from full numerical simulations, and also the growth factor will be decreasing, as in here. See, these were obtained from full numerical simulations, but the advantage of my research is that you don't need to do all this stuff. You can just predict what is happening in terms of stability by just checking your adjusting factors. And this is very you know there are very further works from here. You can apply my technique to many other fluid mechanics problems, and you will get very nice results. You can also verify your results from numerical simulations. So this is very wide. There are many problems waiting for you to investigate anyway. So I'm hoping that new young scholars will enjoy future works of such kind. Thank you very much, Anna. I'm expecting questions from you now.
Thank you very much, Professor Mustafa, for such a nice talk. Are there any questions? Please ask. Dr. Asif, if somebody has questions, just allow him to ask the questions, please.
No, there is no questions. There is no question, in fact, from audience.
Okay, if there is no question, then we thank Professor Mustafa for such a nice talk. Thank you very much, Professor Mustafa.
Thank you. Thank you.
Okay, so our next speaker is Dr. Ahmed Zishan from IIUI Islamabad. He will be talking about the flow analysis between rotating circular plates due to swimming of gyrotactic microorganisms. Dr. Ahmed Zishan. Dr. Ahmed Zishan, can you hear me?
Bismillahirrahmanirrahim. Assalamu alaikum. Thank you, Dr. Mustafa. Thank you, Dr. Yusuf, for introducing me. Uh, can everybody hear me?
Yes, we can hear you. Yes, go ahead, please.
Thank you so much. Thank you, Dr. Yusuf, for introducing me, and thank you, Dr. Mustafa, for a very interesting talk today. It is very knowledgeful for us also. And in my talk, I will be talking about the bioconvection and the movement of the swimming of the gyrotatic microorganisms and uh, between rotating circular plates. Um, Motile gyro microorganisms are also known as gyrotatic microorganisms extensively exist in the splashing environment, which can swim in a specific direction in the fluid. Usually the direction is against the gravity and they move upward, and combinedly they move upward, and in a large number these small organisms move upward against the gravity and uh, created a flow which is called which is named as bioconvection, which is named as bioconvection. The swimming feature of gyrotatic microorganisms are important to understand the different biological phenomena related with bioconvection. The so-called bioconvection nanofluid is to highlight the analysis defines the formation of density stratified and impulsive pattern which in shape by edging the concurrent denser self-propelled microorganisms and buoyancy forces. The usual model of the linear viscoelastic isotropic and incompressible fluids for which the sorry, the study related with the flow, heat, and mass transfer feature of motile gyrotatic microorganism in different geometry has been discovered so far. We are discussing the we are discussing the flow of these motile gyrotatic microorganisms in between the two parallel circular plates which are rotating at an angle at a angular velocity of omega 1 and omega 2, which are described over here, and the two plates are set at z is equal to 0 and z is equal to gamma, a function of t, which is um, the gamma is the squeezing function which tends to uh, change with the time, and the the region between 0 and 1 squeezes with the time. So we define gamma. We define gamma is equal to 1 minus beta t power 1 by 2 into d, and the current work assumed the asymmetric flow of squeezing lubricant film between a couple of finite parallel circular disks. We assume that the coordinates are polar coordinates that those are r, theta, and z, and the associated velocity is velocity vector is u, whose components are u, v, and w. The plate height is defined over here in form of gamma, and we presume that the lower plate is fixed at height z is equal to 0. The upper plate moves with a velocity velocity that is defined by gamma dash. The stationary and the moving plate are retained at a constant temperature, that is T naught and T1, and the constant concentration that are defined as C1 and C. By taking the above mentioned assumption, the continuity equation can be read as equation number 1, and the momentum equation of all three coordinate components of momentum equation are defined as equation number 2, 3, and 4. Here we define the energy equation in equation number 5, with Tc denoted the temperature, C denoted the concentration, Tm denoted the mean temperature, Cp denoted the specific heat, dB is Bromure diffusivity constant, dt, is the thermoporesis parameter or diffusivity coefficient, and QR is basically the radiation component. This radiation heat flux is defined using Rosland approximation and uh, uh, defined by this. And the Taylor series is opened for the first order to get a linear approximation of this temperature. Alpha, E, and beta here are Stephen Boltzmann's constant and the mean absorption coefficient. The concentration equation for nanoparticle can be read as equation number 6 over here, and the conservation of microorganism is defined in equation number 7 over here, where chemotaxis constant is combined with the maximal speed of the swimming and is defined in BW naught, BW naught M naught over here. The initial and the boundary conditions are defined for equation number 1 to 7 by equation number 8 and 9 over here. We uses the similarity transforms defined in equation number 10 and reduces the given equation into equation number 11 to equation number 15, and where squeezing Reynolds number is represented by SQ and rotating Reynolds number is represented by RQ. Bromure motion parameter is represented by TP, thermoporesis parameter is represented by TT, Prandtl number and other parameters are defined over here uh, in equation number 16. The equation number 17 is the reduced form of our boundary condition, and the so-called where F represents the axial and G represent the tangential velocity, theta represent the temperature, phi represent the nanoparticle concentration. Xi represent the motile density microorganism profile, and Xi denote the angular velocity and the range of the velocity between the rotating plates, which is useful to analyze the various flow characteristics of a rotating plate, which revolves in same or opposite direction. Here we define the torque and using equation number 18 and non-dimensionalizing and getting we get the equation number 19. Uh, Solving the problem, we get using differential transform method, we get the results, and here are some discussions about the results. The effect of the squeezing Reynolds number is defined over here, and we can see that the velocity tends to decrease with the rising value of squeezing Reynolds number, whereas the velocity tends to increase with the rising value of Reynolds, rotating Reynolds number over here. And the similar result is defined on the axial velocity due to the squeezing Reynolds number, tangential velocity due to the squeezing Reynolds number. On temperature, we see that the thermoporesis parameter tends to increase the temperature value. Similarly, Bromure motion also tends to increase the temperature when we see the variation with respect to lambda. And opposite behavior has been observed due to the variation of squeezing parameter and squeezing Reynolds number and Prandtl number on temperature. The effect of radiation parameter tends to increase the temperature of the fluid and tend to increase the temperature, and concentration decreases with thermoporesis parameter and increases with Bromure motion parameter. Nanoparticle concentration increases. Nanoparticle concentration increases for the squeezing Reynolds number and decreases for the Schmidt number, whereas the motile microorganism density function decreases with the rotating decreases with the packet number and increases with the rotating Reynolds number. This is only a small study, so here are some references which are helpful in this study. If there are any questions, please ask. Thank you.
Thank you very much for such a nice talk. Are there any questions? If there are any questions, participants can ask question from Dr. Ahmad Zishan. Dr. Asif,
There are
are
no
there any?
questions. No, there is no question.
Thank
Dr.
you so
Yusuf.
much. I try to keep the talk as small as possible because it is online board. I was not really knowing what are the pros and cons of this online mode. Also, I have some issue with my neck, so I try to keep my talk concise.
I think this was a very wonderful talk. We should thank Dr. Ahmad Zishan for such a nice talk. And thank you very much, Dr. Zishan, Ahmad Zishan. And we'll just wait for some time. Our next speaker is Mr. Mohammad Rais. He should be starting at 12:35, but if Mr. Rais is over here, we can start earlier as well. Mr. Rais, are you here?
रईस को यार कुछ Rais, are you there?
Dr. Asif, can you make? I don't know if Mr. Rais is here or not. Rais, can you hear me?
Yes, Rais is here. He will be joining us. Yes. Please start your presentation, Mohammad Rais.
Bismillahirrahmanirrahim. I am thankful to the organizing committee for this opportunity. This work has been done under the supervision of Dr. Matlub Anwar and in collaboration with Dr. Ghulam Fareed. The title of my talk is General Formulation for Error Bounds of Fractional Hermite-Hadamard Inequalities and some example for central moment. This is the overview of this talk. We'll see the summary of fractional integrals. We see the error bounds for generalized integral operator and then generalized integral identity to formulate the existing results. And we'll see the corresponding error bound inequalities from generalized identity. And then we'll show you some application. In this paper, we are going to discuss the error bounds. This is the inequality, which is the classical one named as Hermite-Hadamard inequality given by 1. This is a very classical inequality in the sense that the average integral for a function which is convex can be approximated by these bounds. The error of this bound, this average integral is very important for the researchers. And a lot of paper have been discussed, a lot of publications we have seen which are going to discuss the different versions of Hadamard inequalities by different using different fractional integrals and then the error bounds for these new generalizations of these classical Hermite-Hadamard inequality. The fractional integral operator given in 2 is the classical Riemann-Lively fractional integral operator. and the operator given in 3 is the natural extension of the operator number 2. This operator, which is Riemann lively fractional integral operator, is have been extended by introducing a monotone increasing differentiable function g. This operator is very useful because this can provide a lot of different kernels in the fractional component of the Riemann lively fractional integral. We have footnote and the reference which we have named as 1 is shown in the footnote. Kang et al. Introduced a new extended generalized Mittag-Leffler function given in 5, and they have adjoined the fractional this extended generalized Mittag-Leffler function in the instead of the simple kernel of Riemann lively fractional integral operator to obtain the new fractional integral operator 4. This was the result they have published. This result can be stated that if G is a positive function and G is a Riemann integrable, if G is convex, then the following inequality for fractional integral 4 is holds. Now, recently, Farid, in the paper Existence of an Integral Operator and Its Consequences in Fractional Calculus, have defined the following integral operator by considering g and mu as two functions, where g is a positive and Riemann integral function, and mu is also a differentiable and increasing function. Let rho be a positive function such that the factor rho by x is increasing. Then for x belongs to CD closed interval, the left-sided integral operator is defined by 8. This is an integral operator which can reproduce different kernels which are required for different fractional integral operators. We will see. This is the first deduction. If we consider the function rho by u by considering k gamma function, then the k analog of generalized Riemann lively fractional integral operator is given in 9. If we consider k is equal to 1, then we discovered the G Riemann lively fractional integral. And similarly, if we consider rho of u is equal to this one, then we obtain the new integral operator. This integral operator was discussed by Tunk in the reference which is given in footnote, where f of sigma k of x is a function given in 11, and the coefficient of this function form a bounded sequence of positive real numbers. This is basically the extension of Raynaud's operator. Yes, if we have rho of u is equal to u by gamma exponent minus 1 minus gamma factored by gamma of u, then we get the generalized integral exponential fractional integral operator. This operator was discussed by Dragomir. The reference is given in footnote. And then if we consider rho u is equal to rho u by this function, then we have a natural extension of operator 4, which was given by Kang et al. We have already shown the operator. Recently, Set in the et al. Have introduced a generalized version of Hadamard inequality. This inequality is given in the paper which is cited in the reference. This inequality is given by 14. This inequality is basically the classical generalization of classical Riemann integral, classical Hermite-Hadamard inequality by using the fractional integral operator which we have shown previously. Now, motivated by these papers, we present the following work whose purpose is to develop some generalized error-bound inequalities for the aforementioned fractional integrals. We will use the function g of x is the sum of the two functions g and g tilde, and g tilde is also given by g of c plus d minus x. This is in fact the midpoint type function. This is the now we start our main results. We first have a generalized identity to obtain the error bound, a general error bound. Let mu be a positive monotone increasing function with continuous derivative mu dash on CD. Let g be a differentiable function. If g dash is a Riemann integrable function, then the following identity hold. The identity is given in 15. We'll see the proof of this identity uh, where the function r is given in 16. This function r we have seen in the in space of kernel. This is given by 16. Now, this function is composed of two integrals. This is the first integral we will formulate, and then second integral given in 17. By integrating by parts, we have equation number 18, a very simple calculation, and will lead to 18, and then we have 19, which is the second integral, and using these two integrals we have 21, and similarly we have 22. This will be this has been using the definition of fractional integral operator we have cited previously. This is again a new result. This result has been developed for the generalized exponential fractional integral operator given by Dragomir. We have discussed before in the previous slides. This identity has been developed by 23, where mu is again a positive and monotone function, and the function g is differentiable and Riemann integrable function, and n is also given by 24. Now we have by applying lemma 4 and 5, we have theorem number 6. We will not show the proof of these theorems. We have just applied the application of a modulus of a function in this theorem. If mu is a positive and monotone increasing function with continuous derivative mu dash, if g dash is convex, then the following inequality for the operator 13 holds. And by using lemma 5 and applying the modulus of property of modulus, by considering again g dash as a convex function, we have inequality number 26. Now if we use the classical inequality, holder inequality, then we from lemma 5 have the following inequality number 27. And similarly, by applying the holder inequality on the lemma number 5, we have the inequality number 28. N is also the same function as we have discussed previous in the lemma number 5. To establish a general formulation for the error-bound inequalities, we have following conventions. We have used delta as an integral, where omega is a function defined in 29. Throughout this study, we will use mu and rho as the same function as described in the definition of generalized integral operator given by Fried. This is the lemma which includes all the previous identities for the error bounds of different versions of Hadamard inequalities. Let g be a differentiable function. If g dash is Riemann integrable, then the following equality holds. This equality is given in 30, where delta rho of mu1 is the integral, which is we have shown you. This remark shows that if mu is an identity function, then we have lemma 3 of the result published by Budak et al. And then if rho of u is considered by this function, then we have lemma 2 of set et al., which is given in footnote as reference number 7. If we choose this function rho, then we obtain a lemma 4, which we have already proved. If we consider rho of u as this function, where a is given, then we re-obtain lemma 5. This is the result obtained from for the error bound inequality from the generalized identity. Let G be a differentiable function if phi dash mod is convex on the interval closed interval CD. Then the following inequality for the generalized integral operator given by Fried holds. This inequality also have a good number of consequences. We have re-obtained the results of paper 8 we have cited earlier, and then results of paper 7 of set et al. Now this is the result obtained for the generalized integral identity by using the Holder inequality. This inequality have again the consequences. The results published in the paper 7 and paper 8 are special cases, and we have obtained some new results. The results are also the special cases if we consider the function in 4 and 5 respectively. Now we have some application for the approach we have used. Let x be a random variable whose probability density function is given. Then the mth moment about an arbitrary point x of the random variable x, where m is greater than equal to 0, is denoted and defined by m raised to the power m. This is given in 31. For the random moment of random variable, we have some very nice references. We have focused the reference number 10 by P.O. Muhammad and Sarikaya. Now, by using this function m cap, this is a sum of two functions. Then we have the proposition number 1. Let x be a random variable whose probability density function is psi, uh, and psi is a convex function. Moreover, psi is a convex function on the interval of real number I, such that CD belongs to I and C is less than D. Then we have identity number 32. Now, we have applying the modulus to the previous identity. Let x be a random variable whose probability density function is given and psi is a convex function. Then we have the inequality number 33. This inequality involves the moment of random variable, and this is the function delta is a very general function which can provide different functions by the different choices of row. Now, let x be a random variable whose probability density function is psi, where psi is a convex function on the interval of real number I, such that CD belongs to I with C is less than D, and psi is a Lebesgue integrable function. If psi is bounded, then we have 34. Now, the inequality number 33 and 34. These inequalities can be further deduced for different kernels which can be obtained by using different values of rho, as we have seen in previous results. We have not deduced these results. We have left these results for the interesting readers. In this study, we have obtained some error-bound inequalities for Hadamard inequalities involving fractional integral operators
namely generalized exponential fractional integral operator and generalized fractional integral containing extended generalized Mittag-Leffler function. After obtaining new error-bound estimates, a new and generalized identity is developed. The inequalities emerging from the new generalized identities are surprisingly provide a formulation for existing and new error estimates for different versions of Hadamard inequalities. As we have seen that by different choices of row, we can re-obtain all the previously known results. We have cited them. After this realization, we have focused on the application of these results for central moment of a random variable. Our results are not only generalizing the previous work, but some connections of our results are also been given. We feel that this work can generate a realization among the readers that this approach is useful for the new inequalities in this frame of fractional integrals. We hope that this work will attract the attention of researchers. These are the some references which are very suitable references. Thank you.
Thank you very much. Are there any questions? Dr. Asif, are there any participants who wants to ask any question from Mr. Rais?
No, probably there is no participants who wants to ask some question.
Okay.
So there is one more talk, Dr. Yusuf, after this.
Is it?
Yes, Mr. Rashid Iqbal.
So just right now?
Yes, just right now. He is, he will be promoting, we are promoting him to the panelist. Please wait.
Okay.
He missed his talk yesterday, so we are giving him a chance. So we have some time, 15 to 20 minutes.
Sure.
Mr. Rashid, please start your presentation. Mr. Reis, thank you. You can just sign off.
Thank you, sir.
Okay,
Rashid, please start your presentation.
okay, sir. सर मेरे स्लेट आ रहे हैं आप स्क्रीन पर?
Mr. Rashid, now you can share your screen.
सर मेरे स्लाइड अभी आ रहे हैं स्क्रीन पर? हेलो सर.
नहीं रशीद, आपका नहीं आ रहा स्लाइड. प्लीज आप शेयर करें, स्क्रीन शेयर करें. नहीं आ रही, स्क्रीन नहीं आ रही बेटा.
ठीक है सर, मैं कर.
स्क्रीन शेयर कीजिए प्लीज.
अभी आ रही है सर?
अभी डबल क्लिक कीजिए टू एंटर फुल स्क्रीन. जी स्क्रीन अभी, जी अभी आ रही है नज़र. वेरी गुड. थोड़ा सा इसको बड़ा कर दीजिए, प्लस पे क्लिक कीजिए और इसको बड़ा कर दें. स्क्रीन थोड़ी बड़ी कर दें बेटा.
ठीक है सर, मैं कोशिश कर रहा हूँ. अब सर ठीक है? हेलो सर।
नहीं, अभी तो नज़र नहीं आ रही है ऋषि।
हेलो
ठीक
सर।
है जी, अभी ठीक है। प्लीज़ स्टार्ट योर प्रेजेंटेशन। ठीक है, अभी नज़र आ रही है स्क्रीन, हम सबको सही नज़र आ रही है। प्लीज़ स्टार्ट योर प्रेजेंटेशन।
Okay, thank you. My name is Rashid Iqbal. I am student of MPhil Mathematics from Kuwait University. My presentation title is Symmetry Analysis and Conservation Laws of a Generalization of the Kelvin-White Viscoelasticity Equation. Uh, our layout, motivation, introduction to symmetry, Lee point symmetry, our new work and conclusion. First of all, we are going to motivation. In 1867, a Narian mathematician Lee introduced a powerful technique for the solution of differential equation. The beauty of his technique that is differential equation that is homogeneous, non-homogeneous, linear, non-linear, ordinary, and partial differential equation of order n. Later on, he used this technique for the linearization of nonlinear differential equation, group classification of differential equation, and for finding the invariant corresponding to differential equation. Symmetry. So he was born on 19 November 1842 at Nordfjordeid, Norway. He joined a school in the town of Moss, which is a port in the south, east of Norway. In 1857, he joined Nissen Private Latin School in Christiania, where he decided to join the army, but due to his weak eyesight, he gave up this idea and gave admission in the University of Christiania. In the university, he studied a broad science course. There he attended the lecture of Zeno on the work of Galileus on algebraic equation and the lecture given by Carl graduated in 1865 from the same university without showing any great ability for mathematics or any liking for the subject. But after he made a mathematical career, the first brilliant idea that came to his mind was new geometry by considering curves rather than points only. This idea was further developed after he studied paper on geometry by Plucker and Consulate. Lee composed a short scientific paper on this new idea in 1869 and published it at his own expense. He wrote a more definitive work, but the Academy of Science in Christiania did not publish it. Later on, he submitted it to the Crowley Journal, which it was accepted. He later publication Ray and Lebesh about his work. For the paper in Crowley Journal, Lee said to travel and meet the leading mathematician at the end of the year. 1869, Lee went to Prussia, then Göttingen, and after that to Berlin. And Berlin, he met Kronecker, Komar, and Weierstrass. Weierstrass, who was the leading mathematician of Berlin. But his idea matched with that of Komar. Lee presented his research work in Komar workshop and was able to read a few labs that Komar had made in his work on line congruence. Most important to Lee was that in Berlin he met Felix Klein. It was not difficult to see that these two, Lee and Klein, would, would in fact have the same mathematical background. Klein had been student of Plucker and Lee, despite the fact that he never met Plucker, always said that he felt like a Plucker student, regardless the basic connection through Plucker line geometry. Lee and Klein were somewhat distinctive character as a human and mathematician. The algebraist Klein was fascinated by the peculiarities of charming problem. The analyst Lee, parting from special cases, sought to understand a problem in its appropriate generalization. And Berlin gained confidence in his research. He received a high appreciation from Komar, and he also got answer from Ray and Klebation to his prayer letter, which significantly encouraged him. In the spring of 1870, Lee and Klein met in Paris. There they met Darboux, Chasles, and Camille Jordan, who were the leading mathematicians at the time. Especially Jordan was an expert in Galileo's theory. Lee started to examine these two then on groups and geometry with Klein, and they wrote many papers in the area of research. It was the winter of 1873-74 that Lee developed effectively what is called Lie group transformation. Later on, Kelling and independently investigated the algebra corresponding to these groups, and Cotton completed the classification of semi-simple Lie algebra in 1900. So he was a great mathematician and known as the founder of Lie group analysis. This analysis unified three branches of mathematics, namely algebra analysis and geometry. Lie gained the idea of transformation group from Galileo's theory, which is the group theoretic approach to the solution of algebraic equation. Galileo's theory is shared permutation group to the solution of algebraic equations. Lie applied this idea to the solution of differential equation, and he claimed that there will be groups of transformation associated to the solution of differential equation. The meaning of the meaning of symmetry in a visual sense is the harmonious, beautiful proportion and balance of a body. The reflection symmetry is the simplest one, which in the language of mathematics is called line symmetry or mirror symmetry. As an example, it is easy to observe that apparently one half of a body is exactly equal and of the same shape as the other half of the body. In mathematical language, a beautiful proportion and balance is a pattern self-similarity that can be written in some formal mathematical expression. Formally, symmetry in mathematics is a transformation that leaves the object unchanged. For example, symmetry of function, differential equation, integral equation, etc. are transformations of the variable which leave the function, differential equation, integral equation, etc. unchanged. Lie point transformation, particular case of Lie point transformation. First, translation. The transformation of the form. If we have x and y two coordinate, now if we make a transformation like x bar equal to x plus a, y bar is equal to y plus b, we can add some constant to x coordinate and similarly to y coordinate. Then our new coordinate will be x plus a, y plus b. This is called translation, and x and y axis. These transformation form group called Lie group of point transformation. Next, rotation. The transformation of the form. If we have x y coordinate, now we can go to x bar and y bar. Bar will be x cos of t minus y sin of t. Y bar will be equal to x sin of t plus y cos of t. is called rotation. The area of geometry object remain invariant under translation and rotation. Third one is scale. The transformation x bar is equal to e power a x e power a bar x y bar equal to e power by is called scaling similarity transformation or diagonal. This type of transformation expand or contract the geometrical objects. The expansion or contraction is said to be uniform if A equal to B and non-uniform otherwise. Our new work will be the clean white viscoelasticity equation, the Kelvin white viscoelasticity equation, h of x t q double t minus c of x x into x minus b of x u partial of tx whole x equal to 0. Now we can classify this Kelvin white viscoelasticity equation by geometry. Our first our will be x which is equal to xi xtu partial x plus ta xtu partial t plus phi of xtu partial u. Now we can prolong the generator x to order because our equation Kelvin-White viscoelasticity equation is of order 3. Our generator will be prolongation the form of x plus phi x plus partial over partial u x plus phi t plus partial over partial u t plus phi double x plus partial over partial u double x plus phi x t per partial over partial u x t plus phi x x t partial over partial u x x t. When we apply the generator x t and h, we can get the system of partial differential equation which can be solved easily. Equation 2 gives us the system of partial differential equation. By solving the system, we can get the value of unknown function and the particular value of b of x and c of x, where b of x represents elasticity and viscosity. From here, we find the symmetry for h. Conclusion: Interpol suggested symmetry method for the solution of linear and non-linear differential equation. This method is applicable to both partial differential equation and ordinary differential equation. This method makes our work easy.
If there is any question, the participants can ask. So there is no question. Thank you, Mr. Rashid, for your wonderful talk. Now the session is closed. We have 1 hour break. You just take a lunch or whatever, or maybe relax a bit. The next session will start at 2 o'clock. Thank you everyone for joining us.
Thank you very much.
Thank you, Dr. Yusuf, for chairing the session. Thank you.
No, thank you very much. Thank you.